Hello class, today we want to take a look at Sachs Law and Avogadro's Law. So first let's take a look at Sachs Law. Sachs Law states that there's a direct relationship between the temperature and the pressure of a gas. Once again, the temperature has to be the Kelvin temperature. Pressure can be any of our pressure scales, just as long as you're using the same one for both sides of the problem. And we have to assume that we're keeping the volume constant, so volume can't be changing. So typically we're looking at what we call rigid containers, like things like a steel tank or like a glass container. So steel, metals, glass aren't free to get bigger or smaller, so we got to keep volume constant. So if you look at the formula for Sachs Law, the initial pressure divided by the initial Kelvin temperature is equal to the final pressure divided by the final Kelvin temperature. And if we graph that, as temperature goes up, pressure goes up. So if we triple the Kelvin temperature, the pressure will triple. If we cut the Kelvin temperature in half, the pressure will be cut in half. And that's because as temperature goes up, particles move faster and they're going to collide with more force. So if we put here keep volume constant, and we're going to pump in some gas. Alright, the simulation is a pretty good simulation. I like to use it. This is the Boltzmann simulation. So notice, like before in the last simulation, that's free to move the box, make it bigger or smaller. But this is like made out of steel or it's made out of glass, and we can't do that. So all I can do is I can change the temperature. So notice as I heat it up, the particles are moving faster. And as they move faster, they collide with more force, hit the sides of the container with more force, creating more pressure. So if I heat it up even more, guess what will happen? Alright, so if you throw an aerosol can into a campfire, eventually, you shouldn't do that, of course, but eventually you would hear a pop because the gas particles inside that can give off so much pressure, or have so much force when they collide with the can, that the can will explode. So our container exploded here. So if I reset it, let me pump in some more air. And so this time, once the particles stabilize here a little bit, I'm going to decrease the temperature. Now notice when I decrease the temperature, look how slow they're moving. Alright, so once again, temperatures, the average energy, some are moving faster than others, but overall there's a net slowing of the velocity. Right, so if they're moving slower, when they hit the side here, it's not going to give off as much force. It's not going to create as much force, I should say. Alright, so that's Sachs Law, direct relationship between temperature and pressure. Quick question, going back here to the Deflategate, one of the things that the Patriots said it could happen is they could have inflated the footballs inside, where let's say the temperature is 25 degrees Celsius, that's roughly 80 degrees Fahrenheit. And then when they go out where they played the game, it was colder out, so the footballs would have cooled down to roughly, the freezing point of water, 0 Celsius. So if the pressure starting out inside the football was at the bottom of the regulation, I think the footballs are supposed to be inflated between like 13 and 14. My numbers might be off. It happened a two years ago. So let's just say that 13 is the minimum pounds per square inch of pressure that footballs need to have, and the footballs cooled down. Like, could that have caused the footballs to have deflated and have less pressure? Alright, so P1, so the original pressure is 13 psi. We're going to put that over the original temperature. Temperature has to be in Kelvin, so we're 25 plus 273 is 298 Kelvin. And that is equal to P2 over 0 plus 273, which is 273. So the temperature goes down, pressure is going to drop by a little bit. So 13 times 273 divided by 298. We're looking at a pressure of about 11.9. So pressure could drop by about 1 pound per square inch. But the problem is one of those 12 footballs was still fully inflated. So unless the ball boy messed up on one of them, it does look a little suspicious. But the temperature change could have been a factor in the whole Deflategate scandal. Alright, one more quick law here. And I press the wrong button, so we're going to see a roller pop up, maybe. Nope. Alright, good. Avogadro's Law. Avogadro's Law, if we have two balloons, these balloons are different sizes, so why are they different sizes? So Avogadro's Law says that if we have two balloons that are the same size, and those balloons are at the same temperature and same pressure, the only way the two balloons can be the same size at the same temperature and pressure is if they have the same number of particles inside the balloons. So it doesn't matter what gas is inside the balloons, gases all take up the same space if you have equal amounts of them, equal moles of them, and they're at the same conditions, same temperature, same pressure. So let's say this balloon is 10 liters in size and this balloon is 20 liters in size, and they're both at 1 atmosphere of pressure, and both these balloons are, let's say, at 280 Kelvin. The only way they can be different sizes is if they have different numbers, different amounts of particles on the inside. And so because this one is twice as big as this one, we can conclude that the green balloon has twice as many moles of gas particles inside moving around colliding, creating twice as much collisions, twice as many collisions as this balloon. So if an object's twice as big as another object, if it's a flexible container like this, then it must have twice the number of particles. And it's as simple as that. Alright, hope this helps. Have a nice day.